course EN 203 Digital Electronics and Circuits, and we are discussing the number system. So several number system we have discussed in the previous classes, and for example the hexadecimal number system and how we deal with those number systems, how we go from binary to hexadecimal, and then hexadecimal to binary or hexadecimal to the decimal system, radix, natural radix system. So all these things we have seen, and we have tried to tabulate the digits. Let's say if we write all the decimal numbers 0 to 15, so what we can express in what number system. So taking a 3-bit string which corresponds to the octal number, we have the limitation only up to 7, and taking a 4-bit string which is corresponding to the hexadecimal digit, so we can express up to 15 decimal numbers. So these things we have seen in the previous class. Then we have also seen how to express the negative numbers. So we must have some way to express the negative numbers in terms of the sign and the magnitude. So we have seen a way that okay, one bit can be used exclusively for the sign convention only and nothing else. So without giving any weightage or anything, we can only consider it for the sign, nothing else, and the rest of the bits can be considered as magnitude. This is one way. Another more popular ways are if you take the radix complement of any number. That is one way where you get the complement by using this kind of arrangement, r raised to the power n minus 3, and this can be simplified, that we have seen in the previous class. So we can have the subtraction for the highest integer and then add 1. So that is a simpler way of getting the same thing. And any complement system, when we are discussing, it must fulfill this condition that if you are adding the number to its complement, it must add up to 0, apart from all the extra bits which are getting generated as carry forward. So this rule must be followed in every number system, in every complementary system. So depending on the complementary system, we may have representations for 0 as unique or multiple representations. So we have seen that for the radix complementary system, there is one unique representation, whereas for diminished radix complementary system, there are 2 representations for 0. So this all we have seen. And then we also tried to see how the magnitude of any, let's say, the 16-bit number varies if we plot it against the y-axis. So we see that the highest positive number what is attained is actually 7FFF. This is for the 16-bit number. So same will be true if you increase the number of bits and go to anything. So similarly, you can understand what is the highest value that you can represent in this system. Okay. Now, then we also saw some different number system, let us say some coded number systems, where we are giving some codes for the existing decimal numbers, let's say 0 to 9. So of course, because we have more than 7 units to represent, so we need 4 bits to represent these numbers, and we will have some unused combinations left over. So that is all right. So here what we do, we give a representation of this particular decimal number, let's say 0 to 9, and that we call as binary coded decimal. So the natural binary coded decimal is same as the binary conversion with the weightage of 8421. So simply all these numbers can be converted to binary, and this is called as the BCD, binary coded decimal. Now here the weightage is 8421. We may also have a different weightage. That's what we saw. We may have 2421 arrangement, and the weightage must have the capacity to accommodate the highest decimal number what we are trying to accommodate over here. So this is another way how we can write these decimal numbers in form of the binary coded system. Here the issue is that, for example, if we have the decimal number 5, we may have multiple representations, but we will choose according to our need. So for example, here 5 is written as 1011. Now, using this kind of arrangement is actually giving us the liberty that the number, if you want to get the complement of it, you can simply take 1's complement. So for example, the complement of 5 is 4, and it is simply by changing all the 1's to 0's and 0's to 1's. So that is the way it is convenient for some of the systems. Similarly, we can have another number system which is XS3, where we are simply adding 0011 to the natural BCD, this 8421 weightage BCD, and whatever number is generated, we are simply giving it to that corresponding decimal number. So that is all. I mean, it also follows the complementary system. If you simply replace all 1's by 0's and 0's by 1's, then we can have the complementary number for the particular decimal number. So this all follow, and because of some convenience or something, we always come up with some other way to represent our decimal numbers. So depending on the requirement. Now, when we are having coded decimal systems, we must follow certain rules. For example, when we are adding two binary coded decimals, we must get the output also as binary coded decimal. It cannot be something else. So it is true as long as our sum falls up to 9 or within 9. But the moment this sum goes beyond 9, for example 9 plus 5, we need to make some arrangement, some adjustment to bring it back to the BCD system. So what we do basically, that we have, let us say, even in the decimal system, if we have only one significant bit to represent, the most significant digit is actually a carry forward for the next higher bit. So that is what we do over here also. We have to generate a carry forward for the next system. So we simply add 6 and we adjust it so that it comes back to the BCD form. And then the remaining carry forward can go to the higher bit. So we are following this number system. So these rules are there which we need to follow. Fine, this is all okay. So different number system we have considered and discussed, and something we have got. Now something little more important, that when we are dealing with a different system, binary system, we must have set of rules for that, how we do our processing of these numbers, or how we proceed ahead with, let us say, we want to make some system. So there must be some things which that system want to do. There must be some input and there must be some output. So how do you relate this input and output with each other? So obviously it must be related through some function. So output must be the function of input. So whatever operations you have to do for getting the output, that cannot be exactly same as our natural decimal algebra. Some things we cannot, some things are not possible to do in our Boolean algebra or switching algebra. That's why we need to have different set of rules. Not all are different, but some are different. So first thing what we need to understand for this system is that we have only two values which any variable can attain. And we have given the strict rule that if and only if x is not equal to 0, then only x is 1. And if and only if x is not equal to 1, then only x is equal to 0. So which means there is no ambiguity in this. We are not having anything as average of the two, or something changing from 1 to 2. Let's say it is at 0.8 or 0.9. All this is not part of our logic system here. So strictly whether it is 1 or it is 0, and the transition time as of now we take as 0. Within no time it is going from one state to another state. Theoretically we do not consider that. Understanding my point? Now if we have to define this system, what we say is that Boolean algebra is nothing but combination of these two digits with two the two uh, multiple input, we can say, operations, let's say sum and product, and one unary. That means only one variable is operated with that sign. So you can either indicate by bar or some prime, something like that. So either multiple input operation or single input operation. This is optional. Either you use bar or prime. So is combination of these two bits or these two values and these three operations. That's all. That is what the complete Boolean algebra is. Now, what these operations mean, that we will see. So, already some of you might be aware what this means. Let us say we have two variables and we define this addition or sum, or let us say more specifically to the binary system, we say this operation as OR. So when we are saying OR, which means if either of the variable is true, if either of the variable is having this condition true, which means either of the variable is 1, the output or this OR is going to be true. Or we say even if both are true, let's say 1 plus 1, or you can write 1 or 1, this is going to be true. Clear? This is one of the operation where it is involving multiple inputs, at least two inputs. It may have more also. So the condition that is given by is OR. If any of the conditions, any of the variables are true, then the output is going to be true. Our output is going to be 1. Clear? This is one of the operation. The next operation, which we call as AND, which is also sometimes seen as product, dot or cross, whatever you can give. Here we are not dealing with vectors, so any the representation is fine. So we can say that the output of this is true if and only if both x and y are true. Getting my point? Which means even if any one is 0, either of this thing is 0, our output is not true. It's going to be 0. This is the second operation which needs multiple inputs. There could be more. You can have x, y, z, etc. But the condition is same. This is going to be true. This operation of AND with all the inputs is going to be true only when all the inputs are true. This is the second operation which we will have. Now, the third operation, which is for the single variable or single input, is called NOT, or sometimes it's called inversion or complementary. All these things names we can give, but most popular thing or most popular name given is NOT. So what it says that if you take NOT of any number, then it is 1 if and only if x is 0, and it is 0 if and only if x is equal to 1. So which means only two possibilities are there, right? So if you are at one possibility, after NOT you will change to another possibility. That is all. It cannot have both the things together. The basic rule of our algebra. Clear? Now, yes, of course, we have some representations for these. No, we say representations, then that means when we are trying to implement that, let's say digitally or even in analog circuits and all, when we are trying to implement, of course, we have to have some symbols to represent that. So for example, one symbol is this, another symbol is this, and another symbol is this. So can you name what is this? The first one?
And
Hmm?
And
So the output is x dot y. And here, what is the second?
or
or
So the
x
output
plus y.
is x plus y. And here, of course, it is not.
not.
So we are familiar with all this. There is nothing much to discuss in this. This is a representation given. And again, I have shown only two inputs. There could be more depending on which type of system we are dealing with. But the logic will extend in with the same rule, by the same rule. It is not going to change with number of variables. However, here we cannot have multiple inputs. It is only for one variable system or one variable input. Now, these values, what we are giving, let's say 1 or 0, no, these values given to the variables x, y, z, etc., these are called truth values, or yeah, something we can call. So truth value means what is the value at this moment of this variable. And the combination what we generate, let us say you tabulate x and y, and you generate the output as a table. So the combinations you write over here, because the possibilities are limited, so we can tabulate all the combinations 0, 1, 1, 0, 1, 1. And if this is the function which you are getting at the output, you can simply write by following the rules. X plus y is going to be 0, 1, 1, 1. So this type of combination, when we are representing in a table, this is called truth table, where we are seeing all the possibilities for all the variables, and we are seeing the output, what form or what state it is taking. This is all just terminology, nothing more. So some of you already might be familiar, I am very much sure. So that is fine. Now let us see some more postulates or theorems or something which are more related to our this binary system or algebraic system, this whatever Boolean system or switching system we are talking about. So first rule is we have idempotency, which means if you add any variable to itself, the output is going to be that variable itself without any change. Getting my point? For example, 1 plus 1 is going to be 1. 0 plus 0 is going to be 0. So whatever you add to itself, that is not going to change it. Okay? And the product is also true. If you take product of the same variable with itself, it is going to remain same. Here we don't have the liberty of x square or 2x or something like that. No, all these things are not possible in this number system. Again, you can check 1 into 1 is always going to be 1, 0 into 0 is always going to be 0. So this is the first rule which we have to understand, that we do not have any other option. The variable, if it is added to itself or multiplied to itself, it's going to remain same. This is one property which is different from a decimal number system. We do not have this in the decimal number system, right? Now, some more things. Let us say if you add any variable to 1, the result is always going to be 1. If you multiply any variable to 1, the result is always going to be the variable. if you take sum of any variable with 0, it is always going to be what?
The variable. That variable.
X.
And if you take product with 0, then
X.
0.
Zero.
no matter what x is, now once you have multiplied with 0, the condition of AND is over here. So one condition is already false. So no matter what you do over here, you cannot change the outcome. Similarly, the condition of OR says that if one condition is true, no matter what the other condition is, the output is always going to be true. Clear? These are simple rules, but once we start simplifying our bigger functions, then these becomes little bit important. Now, another thing which is little simpler, but it is all right to mention, the parenthesis rule. If a function like this is written, then the priority is given same as the decimal number system. So this must be read as this and not other way around, x plus y into z, not like this. We are giving priority to this dot operation. Clear? Because many a times you may not find that bracket or parenthesis over there, so you have to apply the rule. Another thing which is again similar to our decimal number system, if you have two variables x plus y, so this is the result is same as y plus x, or if you are taking product of two variables, it is same as y into x. So the sequence doesn't matter over here. In any sequence you add, the result is going to be same. In any sequence you take the product, the result is going to be same. Clear? This is another rule. Simple things, but to say for sake of completion, we have to say this. Otherwise, no bigger things we cannot apply. Now, some more things. Yes, of course, we are doing little bit trivial things, but it's okay. So this is another thing. No matter in what sequence you are adding, if all the things are getting added, that is fine. Same with the product operation also. So this is also true for any case. Now the point comes, let us say if someone asks you how to prove this, then it becomes tricky. Either you have to go with all the exhaustive, some abstract mathematics, or the simpler way to prove is law of induction. Understanding my point? So law of induction says that you make the truth table with all the possible combinations on this side and on this side and see whether the result is matching one to one or not. Clear? So any of these things, what basic theorems we are discussing so far, if you are asked to prove that, you can follow this method for establishing that relationship. Clear? Okay.
Yes.
Now, another simple thing, but very important. If you add any number to its complement, for example, x to x complement, what would be the response? What would be the output?
1.
1. Again, because there are only two possibilities, either x could be 1 or 0. And in any case, we have fixed one of the inputs as true. So the output must be true. Getting my point? If x is 1, then x prime is 0. If x is 0, then x prime is 1. So in any case, we are going to get this output. Now, if you multiply a number with its complement, then
0.
yes.
0.
Clear? So bigger functions, when we have bigger systems to simplify, many a times these situations may arrive. Not with one variable, maybe a combination of variable. Then we can simply use this rule to knock off some of the terms from that function. Clear? Okay. Now, another thing we have to understand is the duality. What duality says that the system what we have, the numbers 1 and 0 are dual of each other, and these two operations AND and OR are dual of each other. How and where to use this we will come back shortly. Okay, just remember this thing, that in this system we have these two as dual of each other. Fine. We'll come to this why and where to use. Now, little bit important, and because someone got this, so they have given it their name also. So that is called De Morgan's theorem. Have you heard about this?
Yes, sir.
Yes.
Yes.
What it says?
Yes, sir.
Yes, sir.
What it says? First thing it says, it's very simple. If you take complement of any system twice or any variable twice, then it comes back to the same value. Isn't it? Because there are only two
Yes, sir.
options.
Yes, sir. Yes, sir.
So if you take the complement twice, that means you come back to the same state or same truth value. Then, little more important, if you have to take complement of this x plus y, then from duality, what we have just now learned, that each and every number and each and every operation can be exchanged like this. So the numbers are the variables are complemented, and the operator, this is also complemented. That is what I was saying as dual. Same is true with x dot y, and if you take complement, this is exactly same as x complement plus y complement. Fine. Now, if we generalize this, this is not only true for just simple functions or simple two input systems and all. In general, any function if you take where you have n number of variables xn, and then some may be exact true values 0, 1, etc., and you may have some operators, and you take complement of this total system, then it is same as if you take complement of each variable, invert, which means take zeros complement 1, 1's complement 0, dual of plus is dot and dual of dot is plus. So exactly replace each element with its dual. Understanding my point? So for any n variable system also, this principle is true. Fine?
Yes, sir.
Yes.
So, and this is same, whatever we have done in this thing previous, these three theorems plus the duality principle. I mean, in fact, this is also following the duality principle. So this is true for any system. Now let us utilize these rules, whatever we have understood so far, to simplify a simple switching function. No? Three variable system, let us say if I give you x, y, z equal to some x plus y, x prime, then y prime z prime is total, then x prime y prime plus z prime. Now can you simplify this using the rules which I have told previously? Just try. Let us see what you are getting. So nothing beyond what we have learned so far. Using that only we have to simplify this.
So 1.
Yes.
1.
So one of the answers, Vardhan, right? Who is that? Vardhan is saying one, right?
Yes, sir.
Okay.
So 1.
Okay. Another option, another answer as one. Who else is getting that answer?
Sir, 1 plus x not y.
I'm asking for the final answer.
So 1.
Okay. That's
Sir,
good.
1.
Okay.
One.
Okay.
Sir, 1.
Okay. Who is not able to get? Honestly, this is not grading something or no giving any marks on basis of this. You can say if you are not able to get it.
Sir, got it.
Okay. So everybody has got. I need not explain this. Anyone?
Sir, I did not get it.
Who is that? Ashwin.
Yes, sir.
Okay. Who else?
Sir, me, sir.
Sir, I also did not got it.
Okay. So good. I mean, this is where you start learning. So it's okay. Let us see what is happening. So some people have got the correct answer, which is 1. This is the correct answer. So you see such big switching function or such big function written with 3 variables and it is coming back to 1, which means this is always true irrespective of how long you are writing this function. What big expression you are writing. So that is where all these rules and postulates and theorems, these are important. So let us see. Let's try to simplify. So obviously, first term we can simplify is this. So we have prime taken of this particular term we can say. So what this would be if you take prime of this? If you follow the duality principle.
X plus y into x plus z.
Correct? Any problem in this? Now what you do, you can take simple product. What is there between this and this term? So some 4 terms would be there. What is x into x?
X.
X.
What is x into y? That is xy. What is y into z? Yz. What is x into y into z? That is xyz. Isn't it? Some simplification we have made. Now we have some, how many? 6 terms are there. So what we can do, you see this. We have x plus xy. So if you take x common, what is remaining? 1 plus y. And what is 1 plus y? 1.
Yes, sir. Yes, sir.
Understanding my point? Again, yz if you take here is 1 plus x. Getting my point? Now, what you are remaining with is x plus yz. And what you have x dash y dash plus x dash z dash. Now, if you just see little closely, these two are actually dual of each other. Isn't it? If you take x common from this, this is x prime into y prime plus z prime. Or you can also write it as x plus y into z whole prime. Now these two terms are exactly complement of each other, isn't it?
Yes, sir.
Yes.
Any confusion in this? This step what I have taken. Now what is the sum of these two? If you are adding any variable with its complement, what is the output?
1.
1. We have not used anything extra than what we have learned. So that is how we can simplify big switching functions or some other complicated forms. So, and we can come up with good reasonable design for the logic circuit. Clear? Yes or no?
Yes, sir.
Okay. So, now we have understood some basic rules and we have also seen an example how to simplify, let us say, a complicated or bigger function. But we are yet to see how to represent any, let's say, a truth table is given. How to represent this in form of function, a Boolean function or switching function. Or if any function is given, let's say set of some 2-3 variables are there, how to write the truth table of that and how to synthesize it. By synthesizing means how will you actually generate the output using this function, using the basic circuits what we have learned, the AND, OR and all these gates and NOT. Using these options, how will we generate the output? How will we synthesize this circuit? So these two things we are yet to learn. Fine. And this is basically your lab exercise 1, which you will be doing on Wednesday, right? So there you will be given some simple things to verify first. That let us say verify the truth table for AND or NOT and all these things. And then you will be given a function that how will you implement this using these basic gates. So this exercise you will do as part of lab exercise. So this portion we will discuss in the next class and we will learn a little bit more about how to express this in a better manner so that we can understand in a concise manner, we can represent this and we can understand that also. Fine. Now coming to the tutorial which happened yesterday. So how was it? Okay, first, any doubts or any questions up to this? Anybody having any doubt, question?
Sir?
Fine. Yes.
I am getting 1 plus and there is some expression of x and y and z. Then I can directly say that the answer will be 1.
Of course, if you are adding anything to 1, what the answer would be?
1 will be.
Fine. So, yeah.